Hello students, welcome to Educate. Today we are going to start third chapter of class 12 physics, that is current electricity. So you have already studied about current in 10th standard. So you have basic idea that like Q equal to N E, Q equal to I T. If you write in terms of differentiation, so you can write dq upon dt is equal to I. Change in charge here per unit time. Suppose you are given charge q equal to 2t plus 3t square, and you want to find out current when time equal to say 1 second. In that case, what will you do? You will find dq upon dt equal to d upon dt of 2t plus 3t square. If you differentiate it, so this will give 2 and this will give 60. Now put t equal to 1, so you will get 8 and unit of current will be ampere. Now here the same basic thing is given. Now electric currents in conductors. So here you know that in case of conductor there are a large number of electrons. So let's read it. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charge particles do exist like upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 power 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound, that is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are particularly free to move within the bulk material. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the current is carried by the negatively charged electrons. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. This point you have to keep in mind. Positive and negative charge both can move. In our discussion, we will focus only on solid conductor so that the current is carried by the negatively charged electrons in the background of fixed positive ions. So this is basic concept. Now let's proceed. Here a conductor is shown, electric field is applied. So what happens when there is electric field? In that case, charge will move. Charge plus q and minus q put at the ends of a metallic cylinder. The electrons will drift because of the electric field created to neutralize the charges. The current thus will stop after a while unless the charges plus q and minus q are continuously replaced. So that is basic concept. Now Ohm's law, if you remember, so it is V proportional to I or V equal to Ri, where R is resistance. And if you remember, resistance can be found R equal to rho L upon A. So this is basic thing. Now further, if we proceed, here some information is given, and now so you know on what factors R depends. So from formula, it is obvious that R is equal to rho L upon A. It means R depends on L are depends on area of cross section, but in inverse way. Same thing is given here, and if we combine, we will get this result. So the same thing is directly written that R proportional to L and R proportional to inversely proportional area. If we combine, then we will get this result. So that is not so important, but you must know. Further, here our concern is to define Ohm's law in vector form. So if you observe, you know V equal to IR. Here everything is scalar. We have to introduce vector here. So if we replace V by electric field, which is a vector, and I by current density J, this is current density, which is also a vector. In that case, the same law will convert into vector form. But for that, you have to check the relation between V and E and I and J. So J, current density, is defined by I upon area, and potential difference divided by length of conductor, here we will take, will be E, right? So we can replace in terms of vector if we want to write. So here we will write it as vector. So we write vector E times L equal to, in place of I, since I equal to JA, so here we take one vector J and we write area times, right, R, and R equal to rho L upon A. So we write that value also here. So vector E times L is equal to vector J times A times rho L upon A. So what is happening? Here L will cancel out from here, A will cancel out from here. So in vector form, we will get E equal to rho times vector J. So this is vector form, where rho is resistivity. And if you remember the relation between resistivity and conductivity, so 1 upon sigma. Sigma is conductivity. So we can also replace this rho by 1 upon sigma. So you will get another relation equal to 1 upon sigma times J, or J equal to sigma E. So this is another form of same law. So I think you have understood. The same thing is given here. So you have, there is no problem. Now we are going to consider what is a drift speed. Drift speed means when electrons move, it collide with different ions, and we calculate average speed. So for that we apply V equal to U plus AT. Here A is acceleration, A equal to force upon mass, and force is, in case of electric field, if charge is there, so it will become QE. So we can write A equal to QE upon M. And initially, suppose electron is at rest, so this U will be 0, and we are considering for electron here, so ME can be written, but and Q can be written as small e. But keep in mind that V being electron, so I'm not writing the scripts. So here we write VD equal to, this is 0, A is QE upon M times this time of relaxation between two collisions. Suppose electron moves to this distance, so time is T. So here we write it as tau, TAU. So this is a relation for drift velocity. Now Q can be replaced by minus E for electronic charge, but it's okay. I have written it in terms of magnitude. Now, here, if we want to relate it with the current density, then what can we do? So for that, I is given by n electronic charge, n times electronic charge, n E a area of cross section into Vd. So we can put the value of Vd. What is Vd here? What we have derived? Drift velocity. As if you take electronic charge, we have derived like QE divided by m times tau we have written. So here in place of Q we can write small E divided by mass of electron into tau. So we can put this value here, I equal to NEA times Vd. Vd is E divided by m times tau. And we can take A to this side. So I upon A, then NE square E upon m times tau. And this is equal to, if you remember, I told you this is current density. So current density J, if you want to write it in vector form, then, and here E can be written as a vector. So NE square upon m tau, these are scalar, and then E is vector. So this is one relation. Now, in terms of conductivity also we can write. So the previous relation, as we have seen here, this is J equal to NE square rho NE square m, and this is tau and E, and we have derived the relation J equal to sigma times E, if you remember Ohm's law, and here we have got J equal to NE square divided by m times tau times E. So this is earlier we have derived this vector form of Ohm's law, and here this is another relation we have got recently. If we compare, what do we get? So here J will cancel out, E will cancel out, so we will get sigma as NE square tau divided by m. So this is sigma, you know, it is conductivity. So we have got the relation for conductivity. The same thing is given here. Very simple picture of electrical conduction reproduces Ohm's law. Now, on the basis of knowledge we have gained up to now, we are going to solve this question. The question says here, estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1 into 10 to the power minus 7 meters square carrying a current of 1.5 ampere. Assume that each copper atom contributes roughly 1 conduction electron. The density of copper is 9 into 10 power 3 kg per meter cube, and its atomic mass is 63.5 unit. Compare the drift speed obtained above with the thermal speed of the copper atoms at ordinary temperature, speed of propagation of electric field along the conductor which causes the drift motion. So let's see how to proceed. So with the given information we can calculate. So first of all, we can write what information is given, and then we can calculate the number density, that is number of electrons in given volume. So here The information is given as area of cross section. It is given as 1 into 10 to the power minus 7 meter square, and the density of copper is given as 9.0 into 10 power 3 kg per meter cube, and other information, atomic mass of copper is also given 63.5 unit. So we can calculate the number density. So number density here, this means in 1 meter cube volume, this much kg electrons are there, and we are to consider only 1 kg of copper. So for that, what do? We can write n equal to, so n will be equal to, so this is atomic mass, which is we can say that this will be equal to 1 mole. So if 1 mole, so in that case it will be equal to Avogadro numbers. So we can say that number density can be found by Avogadro 6.0 into 10 to the power 23 here, and then divided by its atomic mass, so that is 63.5, and then mass is 9 into 10 power 3 kg, and since this is in grams, so 10 power 3 kg into, to convert it into gram, we can write further 10 power 3, and 9 is missing because 9 into 10 power. Now we can evaluate, this comes out to be how much? It will be equal to 8.5 into 10 to the power, if we evaluate, it will become 10 power 28. So this is number density per meter cube. So we have got the value of n. Now we have to find out drift velocity. So if you remember, I equal to NEAVD. So it is simple. Our concern is to get VD. So VD equal to I divided by NEA. We can put the values. Information is given. Current is 1.5. Number density we have just found, 8.5 into 10 to the power 28. And then NE. E is electronic charge, 1.6 into 10 power minus 19, 10 to the power minus 19, into area of cross section. In our question, area of cross section is given 1 into 10 to the power minus 7 meter square. So we can evaluate it. So it will come out to be 1.1 into 10 to the power minus 3 meter per second. So we have got the speed by using the formula. Now our question says that we have to find out its speed by thermal speed of copper atom at ordinary temperature. So to find the thermal speed, what do we need? We need formula. So formula is thermal speed is given by V. Let's denote it T. So in that case, we have to consider Boltzmann constant into temperature and divide by mass. So we put values. So temperature we take 300 Kelvin, and value of Boltzmann constant we can put. So after putting the value, what do we get? If we put here mass of copper, we have to take like 63.5 gram, and when we put all the values, so its velocity will come out to be around 2 into 10 to the power around 2 meter per second, which is larger as compared to the value that we have calculated. Our value was just 1.1 into 10 power minus 3 meter per second square per second, and here it is coming around 2 into 10 power 2, so it is quite big. And then next part is speed of propagation of electric field along the conductor, which causes the drift motion. So there is one basic concept that electric field and magnetic field, they are mutually perpendicular and they travel in form of electromagnetic waves. So here, in case of conductor, the electromagnetic waves will be considered. So its speed of electric field will be same that of speed of light, because light is electromagnetic waves. So here an electric field traveling along the conductor has a speed of an electromagnetic wave that is equal to 3 into 10 power 8 meter per second. So this we will study in next chapter. The drift speed is in comparison extremely small, smaller by a factor of 10 power minus 11, as we have evaluated here. So these things are important. Now we are going to see some basic questions, and they are important. The basic questions are, the first one is, in example 3.1, previously we have calculated drift speed. The electron drift speed is estimated to be only a few millimeter per second. We have calculated it about 1.1 into 10 power minus 3 meter per second. The same thing they are saying, that that is 1.1 millimeter per second for currents in the range of a few ampere, right? Okay, how then is current established almost the instant a circuit is closed? Here question is clear. Question says that drift speed we have calculated is very less, but when we apply potential difference, at once at every point electric field is set up. So what is the cause behind it? So generally what happens here, when electric field is set up, in that case it travels with the speed of, as we have studied, with the speed of electromagnetic waves. So at once electric field is set up. The same thing is explained here. Electric field is established throughout the circuit almost instantaneously with the speed of light, causing at every point a local electron drift. Establishment of a current does not have to wait for electrons from one end of the conductor traveling to the another end. However, it does take a little while for the current to reach its steady value, right? So you have understood that EM wave, speed of EM wave should be considered here. Then next question is, the electron drift arises due to the force experienced by electrons in the electric field inside the conductor. But force should cause acceleration. Why then do the electrons acquire a steady average drift speed? So this is obvious. Let's see the reason here. Each free electron does accelerate, increasing its drift speed until it collides with a positive ion of the metal. It loses its drift speed after collision, but starts to accelerate and increases its drift speed again, only to suffer a collision again, and so on. So on the average, therefore, electrons acquire only a drift speed. So logic is very simple. If there were no collision, in that case, you would have said that acceleration would be there and then force would be there. But here, due to collision, again and again speed reduces to 0, then again acceleration takes place. So like this. And then next question is, next part says, if the electron's drift speed is so small and the electron's charge is small, how can we still obtain large amount of current? So the basic point is number of electrons, they will be very large. So when very large number is multiplied by even very small number, so result will be large. Simple, because the electron number density is enormous. this much, 10 power 29, we have just evaluated the value of N. Then next question is, when electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? So by no means. The drift velocity is superposed over the large random velocities of electrons. And last part is, are the paths of electrons straight lines between successive collisions with the positive ions of the metal in absence of field and in presence of field? So in absence of electric field, the paths are a straight line. In the presence of electric field, the paths are in general curved. So these are some basic questions that you have understood. Now we are going to define another important term that is called mobility. So what is mobility? Mobility, if we denote it as mu, so drift velocity per unit electric field is mobility. So mu for hole, mu for electrons, we can consider. So these concepts we will deal in next chapter, or in case of semiconductors. So here just basic we have to consider. And now if you remember, drift velocity is given by, so what is drift velocity? We have done earlier. Drift velocity is q upon, what is formula from where we derived? So v equal to u plus at, and u we took 0, and this is qe upon m into tau. So this was basic concept. Here if we put this value here, so what do we get? Mu equal to vd, that is qe upon m tau, right? And divide by electric field further, so E will cancel out. So we will get Q upon M times tau, right? So here this is given. Now limitations of Ohm's law. What does this mean? Ohm's law reads as V proportional to I, means V, increase in V will cause increase in current, and we know that graph is like this. If this is V, this is I, so straight line graph. So here we say this is Ohm's law. But suppose it may happen that voltage is increasing, current is not increasing linearly. Situations can be like this. Suppose it is like this, or it is like this. So in such case, we say that there is variation, means there is deviation from Ohm's law. So different type materials are there in which Ohm's law is not valid. So such materials are called non-ohmic conductors. Those materials that follow Ohm's law are ohmic conductors, and those materials that don't follow are non-ohmic conductors. Here graphs of non-ohmic conductors are shown. Let's analyze. Here in this graph, what you observe, this dotted line represents Ohm's law, but here actual line, thick line is deviating. It means there is deviation from Ohm's law. Here different type materials are shown. This material, characteristic curve of a diode. In case of diode, what happens? Up to certain voltage called knee voltage, there is no current, and after that current starts, and even it is not a straight line. So here this will be non-ohmic conductor. Here what you observe, here voltage is increasing, current is decreasing. So there is one interesting point here. If voltage is increasing and current is decreasing, it means resistance will be what? Resistance will be negative. In this region up to here, current is increasing, voltage is increasing, although it is not linear. That is okay, means there is deviation from Ohm's law. But from this point, what is happening? Voltage is increasing, current is decreasing. So this region is negative resistance region. This is important. Sometimes this question comes in your exam. So material that exhibits negative resistance, that is gallium arsenide. Now Let's see some more concepts. So relation between V and I is not unique. There is more than one value of V for the same current here. If you observe at this point, current will be same, but voltages are different. So such a situation we see. So materials and devices not obeying Ohm's law in the form of this are actually widely used in electronic circuits. In this and a few subsequent chapters, however, we will study the electrical current in materials that obey Ohm's law. In case of semiconductor, there will be variation, but in basic chapters, there are certain chapters where there won't be any variation. So resistivity of various materials. Now here we are going to see the dependence of resistivity on temperature. So here graph is shown. This is temperature axis, this is resistivity. This is material copper. So what is happening? Resistivity is varying like this. You should practice this graph. It is important. It starts from here at 0 degree. It has certain resistivity and then resistivity varies. Here also, in case of nichrome, graph between resistivity and temperature is like this. In case of semiconductor, resistivity decreases with the temperature. So here one important term comes into play, that is temperature coefficient of resistivity. Temperature coefficient of resistance also we will consider. So the important relation for resistance, if we write, so resistance at certain temperature is given by resistance at 0 degree and then 1 plus alpha times delta T, where delta T is temperature change, alpha is temperature coefficient. Temperature coefficient. Suppose we want to find out its unit, then how will you relate? So here if you apply principle of homogeneity, this is dimensionless constant. So here these two terms must have no dimension. So alpha must be equal to 1 upon dimension of temperature. And temperature is measured in Kelvin. So alpha must be either in Kelvin -1 or degree centigrade -1. So anything can be used. So the same is true for resistivity. Resistivity at certain temperature equal to resistivity at 0 degree plus 1 plus alpha delta T. So such relations we will study and we will do some numericals based on it. Now, here some important relations are given. We can qualitatively understand the temperature dependence of resistivity in the light of our derivation, that so we have resistivity is rho equal to 1 upon sigma, where sigma is conductivity, m divided by Ne square tau. Tau is time of relaxation, E is electronic charge, N is number density of electron, and m is mass. Okay, so here rho thus depends on inversely both on the number of n of free electrons per unit volume and on the average relaxation time between the collision. Now, as we increase the temperature, then what will happen? Will number of collision increase? Yes, of course. Speed of electron will increase, so number of collision will increase, so collision time will decrease. So average speed of the electrons, which acts as the carriers of the current, increases, resulting in more frequent collisions. The average time of collisions thus decreases with temperature. So one thing will happen. In metal, N is not dependent on temperature, so it will remain constant to any appreciable extent, and thus the decrease in the value of tau with a rise in temperature causes rho to increase, as we have observed. For insulators and semiconductors, however, N increases with the temperature. This increase more than compensates any decrease in tau. So that for such materials, rho decreases with temperature. So what you have seen here, two important facts are there. In case of metals, with increase in temperature, number of collision will increase. So here rho will, what will happen to rho? If this time number of collision will increase, so rho will, this tau will decrease, causing this rho to increase. But in case of insulators, it depends on number also. Sorry, insulators and semiconductors, it depends on number also. In that case, situation will be just reversed. So here, if tau decreases, suppose, then n will increase, but value of n will be very large as compared to tau. So even if tau decreases, n will compensate it and its value will be larger despite that. So tau will, in this case, decrease. So these 2 points are important. You have to remember what happens to resistivity if temperature is increases in case of metal, in case of insulators and semiconductors. So both cases are just opposite. Here we are going to do one question, and what does question say? So question is, an electric toaster uses nichrome for heating element. When a negligibly small current passes through it, its resistance at room temperature is this much, and when the toaster is connected to 230 volt supply, the current settles after a few seconds to a steady value of this much. What is the steady temperature of the nichrome element? The temperature coefficient of resistance of nichrome is able. So as I told you, the relation is RT is R0 1 plus alpha T. Suppose in this case, two resistances are given. At 27 degree, it is this much. And in second case, when the toaster is connected to the current settles after to this value. So again, we can evaluate what is new resistance, and then we can find the temperature coefficient is given. Our concern is to find the steady temperature of the nichrome element. So this can be easily found. So let's see what is resistance in second case. In first case, resistance is given. In second case, we have to find out resistance. So resistance can be found by voltage divided by current. So we have two values. One value we have already got, this is given to 75.3 ohm at 27 degrees centigrade, and this is case when temperature is increased and current settles to 2.68 ampere. So in that case we find resistance. So 230 divided by 2.68 ampere. So this comes out to be 85.8 ohm. Now as I told you the relation, if you start from R2, so R2 equal to R1 1 plus alpha, from this relation RT equal to R0 1 plus alpha T. So if we write it as R2, so this will become R1, then this relation will become 1 plus alpha, and then two temperatures. So T2 minus T1 we can take, and then we can simplify. The same relation they have used here, R2 equal to R1 1 plus alpha T2 minus T1, where alpha is given in our question as this much. So we can put this value. After putting the values, T2 minus T1 will be 820, and we have to get T2. T1 is given in our question as 27 degrees centigrade. So write 27 degree in RHS and evaluate. So you will get 847 degrees centigrade. I think thing is very clear. Now, what is steady temperature of the cycle? That is done. So there is no other part. Now let's go to next thing. Here, electrical energy and power. So power, you know very well, P equal to energy, electrical energy divided by time. and energy can be found, work done. So energy is equal to work, and energy upon time is power. So work upon time, and work if you relate with a charge. So what do you get? So if you here work Q equal to, from potential difference relation, is W upon Q. So W equal to V into Q. So if we write it here, so E upon T is power equal to W can be written as V into Q upon T, and Q upon T is current, charge upon time. So P equal to VI. So this is basic relation. Now here heating effect of current is shown. So heat produced can be found, what is power, etc. So that is simple. But after doing these all things, you will get one important aspect, and that is this. The important point is here. Important point is this. The connecting wires from the power station to device has a finite resistance RC. The power dissipated in the connecting wires, which is wasted in PC with PC equal to, suppose. So what they are talking about, if this is a wire that is carrying current to distant place, in that case, if it has certain resistance, then heat will be produced. Heat will be I square RT, and that will be loss. The same thing they are saying here, that it will be P square. From here, I P equal to VI, so that thing, and V equal to IR, so that thing, or R equal to, here I can be replaced by V upon R, etc. So we will get this relation. So power consumed, that is here the power dissipated in the form of heat, that is given by P is equal to P square RC divided by V square. So here our concern is this V square in denominator. So this tells that power consumed, if voltage is high, then what will happen? If voltage is high, current is low. In that case, what will happen? This denominator will be larger, so this term PC will be less. So that is why when long distance transmission is done, in that case, transmission is done at high voltage and low current. That you will study in a transformer topic, where power will be VI, input voltage, and input current will be product of. So in that case, you will study like E1 I1 equal to E2 I2. So there will be transformer like this, you will see later on, in which this is secondary, this is primary coil, and it will carry current. Suppose this is I1, it carries current I2, and there will be certain terms, number of terms N1, here number of terms will be N2. So in that case, we will get N2 upon N1 equal to E2. Here E2 means voltage in secondary, E2 divided by E1, voltage in primary, and this will be just reverse to current, I1 upon I2. So inverse relations will be there. So we will see in that case, if voltage is high, then current will be low. So for transmission, as we see that if voltage is high, in that case, power loss will be less. So here the same thing is given. To drive a device of power P, the power wasted in the connecting wires is inversely proportional to the square. The transmission cables from power station are hundreds of miles long, and their resistance RC is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for high voltage danger signs on transmission lines. A common sight as we move away from the populated areas. Using electricity at such voltage is not safe, and hence at the other end, a device called transformer lowers the voltage to a value suitable for the use. So I am going to tell you little more about transformer. So there are two types of transformers. Like one will be step up. So step up means here this is number of turns, say this is N1. Here there are laminated plates, and here there are number of turns, say N2. If N2 is greater than N1, in that case it will be step up. And what will happen? Input voltage, suppose this is V and the terms ratio. So out, say this is V1, this is V2. So V2 upon V1 will be equal to N2 upon N1. And if number of N2 is larger than N1, so definitely V2 will also be larger than V1. So this is how voltage can be raised to certain value. So this is called a step up. And just reverse, suppose number of turns here are more than the number of turns in secondary. In that case, this will be, suppose this is N1, and here what we have assumed, N2 is greater than N1. Here N1 and N2, what is relation? N1 is greater than N2. In that case, voltage will be reduced. High voltage will be converted into low voltage. Here low voltage is converted to high voltage. So these are all things we will study later on. So up to here, I think you have understood. In next lecture, we will study cells, EMF, internal resistance, and terminal voltage, etc. Thank you for watching. Team Educate.